All right, in this section, we're going to learn a new technique of integration, one that we have not seen in Calc 1. It will allow us to integrate functions that look like these three here. It's like we're multiplying things, we're multiplying functions. Usually we might use it when we have one factor that's algebraic, like that it just involves powers of x, and another function that is transcendental, like ln or e to the stuff or sine or cosine, and then we can even use it on integrals like we have at the end here, where we have the product of two transcendental functions. You might notice, if you take a look or even give it a go, like a simple u substitution won't work on these. So we'll begin this section by just deriving Theorem 9, what we know as what we know as integration by parts, and it comes from the product rule in differentiation. So remember from Calc 1, and we've used it in this course also, that the derivative of the product of two functions, so if u and v are both functions of x, then if I want to take the derivative of u times v, I take that is given by the function u multiplied by dv dx plus the function v multiplied by du dx, or sometimes you might see it written in the prime notations like we have here. So I'm going to begin this process just by rewriting this top line here, right? So here's the product rule. So we have this equation, and the next thing what we'll do to this equation is integrate both sides with respect to x. Now on the right side, we're integrating a sum, so we can split this up over addition. And you could see we actually kind of get these dx's to cancel. So we have the integral of u oh, that should be a dv. I wrote that wrong here. We have the integral of u dv plus the integral of v du, and this is on the left side of this equation we have the integral of the derivative of u times v. So the integral of the derivative, those two things cancel each other out, right? Integration is sort of an inverse operation to differentiation. So on the left side, we've got u times v. And the last part that we're going to do here is we're just going to subtract the integral v du from both sides, right? This last integral on the right side. And when we do that, if we just solve this equation for integral of u dv, we get integral u dv equals u times v minus the integral v du. And this is integration by parts. So it tells us how to integrate something that looks like u times dv. So it requires us to make substitutions, right? We have to look at the integral and say, okay, this is my u and this is my dv, and it has to be, those choices have to be such that u times dv is what shows up in the integral. And if that's the case, then integration by parts allows us just to rewrite that integral in terms of another integral. The idea, our hope, is that this other integral is one that we know how to do. Now, because we're making some substitutions, there are choices that we have to make. You know, so in that case, you know, it could take a couple of tries, 2-3 tries to find what works, you know, what kind of partition of factors works for u and dv. Some general guidance is that dv has to be something we know how to integrate, right? So we're making a choice. This is u, this is dv. Once we make those choices, then we find du from u, and we have to find v from dv. So we have to know how to integrate dv. And then also another general guideline could be that, if u is something that gets simpler when we take its derivative. Like if u is a power of x, when you take its derivative, then you get a smaller power of x. So that can be a guideline as well. But dv always has to be something that we can integrate. So let's do an example. We're looking at the integral of x times e to the x dx. And we need to pick something for u, and we need to pick something for dv. So in this problem, just to kind of show you the basics of how to work, I'm going to let u equal x, and I'm going to let dv equal e to the x dx. Notice that dv always includes the dx. And now from each of these, I'm going to find du and v respectively. So if u is equal to x, then du is equal to just dx, right, or 1 dx. So that's something that certainly gets simpler when you take its derivative. And dv, if we're going to find v, we have to integrate. Now, as we're going to integrate it as a function, but when you integrate it, you just take the simplest antiderivative. We don't worry about a plus c in this process. So v is the integral of e to the x dx. We take the simplest antiderivative, and of course e to the x is its own integral. So v is equal to e to the x. Now we can set this up. I always begin an integration by parts problem by just writing out what the integration by parts formula is. So this will be u times v minus the integral v du. So u times v is x times e to the x minus the integral of v du. So that's e to the x dx. So this doesn't finish the problem for us, but we've now rewritten it as this expression that involves an integral we know how to do. We can integrate e to the x dx. We just did it in this setup. So let's finish this up. X times e to the x minus the integral of e to the x is still e to the x plus a constant. And we can make this, I guess, a little bit simpler if we just factor out an e to the x. So there's our result, is e to the x times x minus 1 plus a constant. So let's try another one. Maybe you want to pause the video now and see if you can guess or have a try at what you might pick for u and dv before I tell you what I'm going to pick. Here, I'm going to let u equal ln x. Now, you might be thinking, why would we let u equal ln x? That doesn't necessarily get simpler when we take its derivative. Before we use the power of x, because powers of x definitely get simpler when you differentiate. And the reason that I'm letting u equal ln x is because I can't let dv equal ln x dx, because we don't know the integral of ln x. Like, that's just not an integral we know. So remember that dv has to be something we can integrate. So I'm going to let u equal ln x, which means that du is 1 over x dx. That means that dv has to be the remaining factors, which will be the x squared dx. And so to find v, we're going to integrate x squared dx, and just take the simplest antiderivative. That's 1/3 x cubed. Now let's put this together. Again, I'm just going to write out the integration by parts formula. That'll be u times v minus integral v du. So u times v is ln x times 1/3 x cubed minus the integral v du, so it's 1/3 x cubed times 1/x dx. So integration by parts, again, just allows us to rewrite the integral in terms of another integral, and now we're just going to try to attack this problem. And this one can be done most simply, I think, first by doing some algebra. I'm going to yank this factor of 1/3 out and then simplify using rules of exponents there. So we've got our 1/3 x cubed times ln x minus 1/3 integral. When I cancel that, we get an x squared dx in the integral, and we know how to integrate that. So let's do it. We get 1/3 x cubed ln x minus 1/3 times 1/3 x cubed plus a constant. And just rewriting this one more time, 1/3 x cubed ln x minus 1/9 x cubed plus a constant. Okay, let's try another one. This integral, we want to integrate arc sine x dx. So a couple of things. One, we can see that we're finding a definite integral. We've got limits there. I'm going to approach it just by finding the indefinite integral first. Once I have that, I'll know what to throw my limits on. Also, the other thing you might notice is it doesn't even look like a product. We've just got one factor, arc sine x. Now, in this case, and really in all cases, dx is part of these factors. So you can still see this as a product, as arc sine x times dx. And so in this case, we're just going to let dv equal dx, which means u is equal to arc sine x. So let's let u equal arc sine x. That means that du, using the formula for the derivative of arc sine, is 1 over the square root of 1 minus x squared dx. dv is equal to dx, and so that means v is the integral of dx, and of course that simplest antiderivative, v is just equal to x. So now the integral, the indefinite integral, arc sine x dx, is equal to, I'm going to start by writing out the integration by parts formula, u times v minus integral v du, and u times v is arc sine x times x. I'm going to write the factor of x in front just so it doesn't look like the product is inside the function, minus the integral v du. That's going to be x times 1 over the square root of 1 minus x squared dx. Now we just have to see if we can integrate this function. And on this integral, maybe you want to pause the video before I tell you how I'm going to approach it, and give it a go yourself. For this integral, a simple u substitution will work, and it is a power rule integral. So we're going to let, in this case, it's like making another u substitution where our u, or I guess I could call it u2, is equal to 1 minus x squared. I'm just going to rewrite this in a power rule friendly form. 1 minus x squared to the negative 1/2, and we have x dx. In order for its derivative to be showing up in there, I need a factor of -2. I'm going to compensate by putting a factor of -1/2 outside. So we have x arc sine x minus, oh no, I guess that'll be a plus now, 1/2 times, and if I use the power rule, I'm going to have 1 minus x squared to the positive 1/2 times 2 plus a constant. These will cancel. And simplifying this a little bit, we get x arc sine x plus the square root of 1 minus x squared plus a constant. Now we're doing this so that we can evaluate the definite integral. So this definite integral from 0 to 1 of arc sine x dx is equal to this function we found. Plugging in the upper limit, and then the lower limit, so let's see what we got here. Arc sine of 1, sine is equal to 1 at the top of the circle, so that's pi over 2. This is 0. This is 0 because there's a factor of 0. Also, arc sine of 0 is 0. And of course this is equal to 1. So we have pi over 2 minus 1. Alright, let's do another one. As the kind of introduction to this problem suggests, sometimes we might have to repeat the process. So I'm going to kind of show you how that works here. Now, in this case, I'm going to go ahead and pick u equal to x squared. That does in fact get simpler when you take its derivative, and we know how to integrate sine. We know the integral of sine x. So we're going to let u equal x squared, which means that du is 2x dx. We're going to let dv equal sine x dx, and that means that v is equal to, the integral of sine is negative cosine. So let's put this together. U times v minus integral v du. U times v, so if I multiply u times v, I get a negative x squared cosine x minus the integral of v du, so that's negative cosine x times 2x dx. I'm going to simplify this other integral, really just going to pull out the 2 and the negative. So it looks like this, x times cosine x. So when we use integration by parts, right, after we kind of put this together using the formula for integration by parts, then we just focus on this new integral and say, oh, do we know how to integrate this? And in this case we have another function that is like an algebraic factor times a transcendental factor, the cosine x factor, and a simple u substitution won't work. So we'll use integration by parts again. Now I'm encouraged and feel like I'm still, even if I'm using integration by parts again, I feel like I am making progress because at least I'm starting out with a lesser power on x here. So I'm going to, in this integral, pick another u substitution. So I'll say this is the first one, and this is the second one. Be careful, I am abusing the notation a little bit since I'm using u and v and dv again in the same integral problem. So if u is cosine x, then du is negative Oh wait, sorry, I need to make a different choice there. We know how to integrate cosine, so we're going to make the similar choice as we did in the first round. We're going to let u equal the power of x. So u is x to the first. That means du is equal to dx. Our dv function is cosine x dx, and if we integrate that, we get sine x. So let's put this together again, kind of just bringing this down, minus x squared cosine x plus 2 times, and it's this integral I'm using integration by parts on, so I'm just going to write this out again, u times v minus the integral v du so u times v is x sine x minus the integral v du is sine x dx. Now I'm feeling pretty good about this because this integral is one that we do know how to do. We don't have to do another round of integration by parts. Let's see, I'm going to let's see, just so I don't do too many steps at once and make a mistake, I'm going to just distribute this 2 first, and then I'll do the integration. So we know the integral of sine is a minus cosine, and since we are subtracting this integral, it'll end up being a plus 2 cosine x at the end there. And then plus a constant, of course. Okay. Alright, so this next one, this one's a little bit different than the others. I just want us to first observe there's no algebraic factor. I've got no powers of x or square root of x or anything like that. I've got 2 transcendental factors. I've got an e to the x multiplied by a cosine function. This problem I'm going to put squarely in like the party trick category of mathematics. So get ready, this is going to be pretty enjoyable. In this example, in this integral, I'm going to go ahead and I'm going to let u equal cosine 2x. So that means that du is equal to negative 2 sine 2x dx. Our dv function then is e to the x dx, and with that selection, everything in the integral is accounted for, is equal to u times dv. And so v is the integral of this, or the simplest antiderivative, and that is e to the x. Alright. Let's put this together. Our integration by parts is u times v minus integral v du. Let's plug this stuff in. U times v, that'll be e to the x times cosine 2x minus integral v du. So I'm going to write this as a minus 2 e to the x sine 2x dx. And I'm going to drag this factor of negative 2 outside. So we have plus 2 integral e to the x sine x 2x dx. Okay. Now, this integral that we're left with, right? I mean, we do integration by parts in the hopes that the integral that we end up with is one that we'll know how to do. This is kind of similar, not too far from the one we started off with, right? It's just that we have a sine instead of a cosine function. So, we're going to use integration by parts again here. Alright, so here's the first iteration of integration by parts. Here's the second one. I'm going to let u equal sine 2x. So then du is 2 times cosine 2x. Then our dv has to be e to the x dx. Same choice as our v in the last iteration, and so v is still e to the x. All right, let's throw this in. So this is u times v minus integral v du. Let's plug in our expression. So u times v is e to the x times sine 2x minus the integral v du is going to be 2 e to the x cosine 2x dx. Now I'm going to do a couple of things here. I'm going to pull out this factor of 2. I'm also going to distribute this factor of 2 at the same time. So we have e to the x times cosine 2x plus 2 e to the x times sine 2x. And this will be a minus 4 integral e to the x times cosine 2x dx. So, let's take a look at what we got here. We started out, right, all of this is equal to, right, the integral of e to the x cosine 2x. I've used integration by parts process twice, and we have the very same integral showing up. It looks like we just went in a big circle, right? And like we started out, we ended up where we started, and you might be tempted to kind of throw in the towel at this point, but I'm here to tell you this is exactly where we want to be. This is actually super convenient for us. So I'm actually going to do some magic here on the OneNote to give myself some space on the left here, because I just want to remind myself this is equal to the integral of e to the x times cosine 2x dx. Now we have an equation. Let's just use algebra now. We'll solve this equation for that integral. I'm going to add 4 times the integral of e to the x times cosine 2x dx to both sides. So we have now 5 times the integral e to the x times cosine 2x dx is equal to e to the x cosine 2x plus 2 e to the x sine 2x. And now all we have to do is divide by 5. It almost feels like cheating. It feels like we didn't have to do any integration. But if we divide through by 5, we get integral of e to the x cosine 2x dx equals 1/5 e to the x cosine 2x plus 2/5 e to the x sine 2x plus a constant. It's almost like we integrated this function using mirrors or something. But it's super slick. Definitely a party trick. Alright, let's try another one. This will be pretty, I think, satisfying and a little bit fun to do. We want to integrate secant cubed x dx, and we have different ways we could pick our factors. You could think of it as having 3 factors of secant there and a dx. We know the dx has to be included in the dv. Also, dv has to be something we know how to integrate, and ideally something that's not like terribly complicated to integrate. So I'm going to let u equal secant x. We know how to integrate that. The derivative of secant is secant tan. That means now that dv has to be the rest of the factors. So that's secant squared x dx. And if that's dv, then its integral, or the simplest antiderivative, is just tan x. Okay, now let's put this together. U times v minus integral v du. And that is secant x tan x minus integral v times du. That'll be tan squared x times secant x. So at this point we can, we're looking at this integral that we end up with, right, and trying to see how we can integrate this. So there's not a simple u substitution that'll work. If it were a tan times secant squared, we'd be a lot happier. A little u substitution would work there, but it's not. It's tan squared times secant. That makes it a bit harder. So to continue working with this integral, I'm going to use Pythagoras here. So remember that sine squared theta plus cosine squared theta is equal to 1. If we can divide through by cosine squared theta, and we get tan squared theta plus 1 equals secant squared theta. And that means that tan squared is equal to secant squared minus 1. Alright, so we're going to use this identity here and make a substitution right there. Alright, so we've used that identity. I'm going to next distribute this factor of secant. I'm going to distribute that factor of secant and then I think split up the resulting integral. So we have minus integral secant cubed plus, don't forget we have a double negative here, so it'll be a plus integral secant x. We know the integral of secant x. That's one of the formulas that we don't need to memorize or anything, so I'm going to throw that in. So now we have secant x tan x minus integral secant cubed x dx plus ln of absolute secant plus tan. So all of this is equal to the integral of secant cubed x dx. And we see the integral of secant cubed x dx show up again in this integral, in this iteration of integration by parts. So just like we did in the last example, we're going to finish this problem by using algebra. Let's add the integral of secant cubed x to both sides. So now we have 2 integral secant cubed x dx is equal to secant x tan x. plus ln of absolute secant x plus tan x. And now all that's left is to divide both sides by 2 or multiply both sides by a half. So we get integral of secant cubed x dx is 1/2 secant x tan x plus 1/2 ln absolute secant x plus tan x plus a constant. Now that's a pretty satisfying integral. The last thing we're going to do in this section is look at what we call the tabular method for integration by parts. Some of the problems that require us to use integration by parts more than once. And I'm not talking about these fun ones where we end up having to finish with algebra. I'm talking more like this problem here, right? We had to use integration by parts twice before we ended up with this integral down here that we just knew how to do. In integrals like that, we can organize this work in a table that'll make our work a little bit easier. It works particularly well if you have a power of x multiplied by like a sine of a constant times x, or cosine of a constant times x, or e to raised to the power of a constant times x. So like one of these three forms here. So here's how the tabular method works. I'm just going to show you by example. We're going to make 3 columns. The first column, we're just going to toggle between plus and minus, and it always starts out with plus. The next column is going to be our choice for u, and then we're just going to keep taking the derivative of that down the column. And our last column is going to be our choice for dv, our initial choice for dv here, and we're just going to kind of integrate or write down the simplest antiderivative as we go, kind of in an iterated process. So in this tabular method for these types of integrals, you always let u equal the power of x. So u is equal to x squared, and I do this first column, or the middle column here first. Take the derivative, we get 2x. Take the derivative again, we get 2. Take the derivative again, we get 0. That's how I know that's where the process will terminate. So I don't have to go any further than that. I'm going to now jump to the very left column just to put in the rest of these signs. So we always start with plus, minus, plus, minus. Now if u is x squared, that means dv was the sine of 4x dx. So I'm just going to write the sine 4x part. And we're going to integrate. Now because it's a constant times x inside the sine function, the integration part is pretty simple. You could work out the details if you want to like make the u substitution explicit where u is equal to 4x, but it's fairly simple. The integral of sine is a negative cosine, and then we have to kind of accommodate that factor of 4, so it'll be a minus 1/4 cosine 4x. You can check by making your u substitution. You can also check and convince yourself by just taking the derivative of negative 1/4 cosine 4x, and you will see that you do get a positive sine 4x. We'll do that again. The integral of cosine is sine, so this minus sign comes down with us. We need another factor of 1/4, so it would be 1/16 sine 4x. And now the integral of sine again is negative cosine, and so that'll switch the sign again, flip it to a positive. We need another factor of 1/4, so we get a positive 1/64 cosine 4x. Okay, so now we're done filling in the table at this point. And the way we put it together is we form some products and then add them together. And those products are, you take the positive x squared and then you go down 1. So our first term is let's see, it'll overall end up being a negative 1/4 x squared cosine 4x. Then this next product we take the negative, we have 2x times a negative 1/16. This will end up being a positive. Two times 1/16 is 1/8, so it'll be a positive, well, I'll just kind of write out the product itself. 2x times 1/16 sine 4x. And then our last product here is a positive 2 times 1/64 cosine 4x. Now we're just going to add these up. And I'm going to just simplify those last two products as I go. So this ends up being negative 1/4 x squared cosine 4x. That'll be a plus 2 times 1/16 is 1/8, so 1/8 x sine 4x. Plus 2 times 1/64 is 1/32 cosine 4x, and then of course plus a constant. And that's sort of how we can simplify the process. Again, the tabular method really works best in integrals of those forms where one of our factors is just a power of x, like a positive integer power of x, and the reason is because this table eventually will terminate because those derivatives will eventually get to 0, where you let u equal x to some positive integer power.